All right. Welcome, everyone, for the second session of the day. Please, if everyone can take their seats. Thank you, Ben. All right, so let's kick things off with the first talk of the session. It's by Pragya Chawla. It's an invited talk on observational constraints on FRB progenitors. I'll give you a 5-minute warning, Pragya. Take it away.
Thanks, Jakob. Hello, everyone. I'm Pragya Chawla. I'm a postdoctoral researcher working at the University of Amsterdam with Professor Jason Hessels and the AstroFlash group. Today, I'll be reviewing the recent observational results on FRBs and how they can place constraints on the progenitor models that have been proposed to explain the FRB population. So I'll start with giving a summary of the proposed progenitor models, then move on to describe the constraints from individual sources, so sources such as the first repeating FRB or the first periodic FRB. Then I'll describe constraints arising from studies of multiple sources or from a large fraction of the population, focusing specifically on propagation effects, subarc second localizations, and host galaxy properties. And in the end, I'll discuss some observational avenues that we should preferentially focus on in order to develop a clearer picture of FRB progenitors. So the first constraint that we have from FRB observations is that the FRB pulse widths constrain the size of the emission region. So the emission region should be smaller than the pulse width multiplied by the speed of light in order to not violate causality. For an average FRB with a width of a millisecond, this means that the emission region should be smaller in size than 300 kilometers. This constraint, of course, favors compact object progenitors. However, there is one caveat here, that the size of the emission region could be larger if the emission is instead caused by relativistic plasma. The other constraint that we have is from FRB repetition. So cataclysmic models are ruled out at least for repeating sources of FRBs. However, we cannot safely yet apply this constraint to the entirety of the FRB population, as we are still unclear if repeating and non-repeating FRB sources have different progenitors. Some properties are different between repeating and non-repeating FRBs in that repeaters have longer widths and narrower bandwidths. However, these properties could be explained by different emission mechanisms or propagation effects and do not necessarily require invoking different progenitor models. So over 50 models have been proposed to explain the FRB phenomena. In the interest of time, I'll not be going through each of these models in detail, but I'm broadly grouping these models into different categories based on the type of the progenitor that the model invokes. So we can start with isolated neutron stars. The detection of radio emission from a neutron star at gigaparsec distances requires stars that either have millisecond rotation periods or really high magnetic fields, depending on whether the neutron star is rotationally or magnetically powered. These models can also be grouped into two different subclasses based on whether the FRB emission is being generated in the magnetosphere of the neutron star or in a relativistic shock in the surrounding medium. And of course, these models allow for repetition. The next class of models, the compact object mergers, do not allow for repetition and include mergers of neutron stars, black holes, white dwarfs, or any combination of these objects. We could expect potential counterparts in the cases of these models, such as short GRBs, gravitational wave signals, or a type 1a supernovae, if one of the merging objects is a white dwarf. The main issue with this class of models is that the volumetric rate of non-repeating FRBs exceeds that of compact object mergers, suggesting that a large fraction of FRBs must repeat and therefore cannot come from this class of models. The next category of models are the interaction models. This could involve interaction between a neutron star and an asteroid belt or the wind of an orbiting stellar companion. FRBs could also be powered by flares from accreting neutron stars or black holes in binaries. This class of models can explain the repetition of FRBs, and in addition can also explain the periodic activity because you'd see a periodicity at and a phase modulation because of the orbit. There are also some more exotic models, such as neutral or superconducting cosmic strings, axion stars interacting with neutron stars, or novae of exotic objects. I've, of course, not covered all of the models here, so you can refer to FRBtheorycat.org for a more comprehensive summary of these models. Now I'll start with describing the observational constraints that we have on the progenitors, specifically focusing on the individual sources. So the most important source that has helped in this regard is the galactic magnetar, SGR 1935 plus 2154, from which an FRB-like burst was observed in the year 2020. The dynamic spectra of this burst is shown on the right, with detections made with the CHIME telescope as well as the STARE-2 radio array. This burst had an inferred energy of 10 raised to the power 34 ergs, making it 1,000 times brighter than radio pulses from any known magnetar. More radio bursts with lower fluences were also observed from this source, with the burst energies from this source now spanning about 7 orders of magnitude. The brightest burst, so the one whose dynamic spectra is shown here, had an energy that was 30 times lower than that of the weakest bursts from a known FRB. And this has reduced the energy gap between magnetar bursts and FRBs considerably, suggesting that magnetars produce at least some FRBs. So of course, this observation supports the model where you have isolated neutron stars. The volumetric rate of FRBs under some reasonable assumptions about the active age of magnetars, as well as the magnetar birth rate, is potentially consistent with that of magnetars. However, the repetition rates of the most prolific repeating FRBs cannot be explained by SGR 1935 plus 2154-like sources. This is shown in the plot on the right that has repetition rate on the y-axis and energy on the x-axis. The repetition rate that is inferred based on the detection of this one burst from SGR 1935 is orders of magnitude lower than the repetition rate for the most prolific repeating FRBs, suggesting that we need more active or younger magnetars to explain the known repeating FRB population. And that's just because magnetar activity increases with increasing magnetic field and a younger age. The next most important observation that has placed constraints on FRB progenitors is the periodic activity in repeating FRBs. So FRB 2018-0916b was found to be periodic with a 16.35-day modulation and a 5-day long activity window. The plot on the right shows the exposure time of the CHIME FRB instrument on the y-axis and the time that the observations have been conducted on the x-axis. As you can see, all of the bursts from this source were detected within these shaded gray regions, which correspond to the 5-day long activity windows. A potential periodicity of 160 days was also observed in FRB 2012-1102A. This source has a much larger duty cycle, so about 50%. And a similar plot for this source is shown here on the bottom left. As you can see, all of the bursts from this source lie within the yellow shaded regions, which are the activity periods for the source. Now, in order to explain the periodic activity in repeating FRBs, we can invoke different phenomena. So you could start with rotation. So the rotation of the neutron star, it was causing the FRB signal to be modulated with this period. However, galactic magnetars have periods less than 12 seconds. We could slow the magnetar down enough and by transferring away angular momentum using particle winds, giant flares, or fallback accretion. This would be feasible for the 16-day period. However, a 160-day period is difficult to reconcile with this model. The other model that was invoked is precession. So if we have a freely precessing magnetar combined with an isotropic flaring activity, that could result in a modulation of the burst rate, as is shown in the illustration here on the right. However, this model also has the same issue in that precession is either on the scales of hours to weeks, and a 160-day period is again difficult to reconcile with these models. So the most probable model for this source is binary motion. So if you have a neutron star that's interacting with the companion wind or an asteroid belt, then you could have phase-related emission with the 16-day periodicity corresponding to the orbital period. The next important observation is that of persistent radio sources. So we had like the first persistent radio source detected from an FRB, 2012-1102A. The plot here shows the image from an EVN observation with the persistent radio source at the center and the location of the FRB indicated by the black cross. This source is found to be compact, less than 0.7 parsec, and is located in a dwarf galaxy. More recently, a persistent radio source was also found to be associated with FRB2019-0520b. Again, this source is also in a dwarf galaxy, but has a very high host or local DM of 900 parsec per centimeter cube. However, other repeaters are not associated with persistent radio sources, and we have very strict limits for some sources at least. So the PRS associated with FRB 2018-0916b, the periodic FRB with a period of 16 days, is at least 400 times fainter than that associated with FRB 2012-1102A. There are several models which are consistent with generating persistent emission. I'm only listing two here, as these can also explain the large but decreasing rotation measure of FRB 2012-1102A. These models include a young millisecond magnetar powering a decades-old supernova remnant, or a radionebula from a hyperaccreting X-ray binary. More recently, we had the observation of a sub-second periodicity in FRB 2019-1221A. This source was detected as having a period of 216.8 milliseconds with the CHIME FRB telescope. The plots here show the dynamic spectra of the bursts with 9 different subbursts. Again, frequency is on the y-axis, time is on the x-axis, and the integrated time series is shown here in the bottom plot. This periodicity of 216.8 milliseconds suggests a neutron star origin for this source. So models with isolated neutron stars, as well as those with a neutron star in a binary, are compatible with this source. Moreover, this source has not been seen to repeat in 400 hours of exposure over several years of the CHIME FRB experiment. Therefore, a compact object merger explanation might also be viable for this source. This source might also be different than other FRBs in that it is the only FRB confirmed to exhibit periodicity. There are 2 other low significance detections in the CHIME FRB sample, but none as convincing as this one. So another recent observation that has helped us ascertain the nature of FRB progenitors is that of FRB 2020-0120E. This is a low DM CHIME FRB repeater that was localized to a globular cluster in M81. Globular clusters typically host old stellar populations, so this rules out a neutron star that was formed through core collapse. Isolated magnetar models are still viable if the magnetar is formed via a special formation channel, such as accretion-induced collapse or a merger. A compact binary system could also explain the source, especially considering that compact binaries are easily found in globular clusters. The image on the right is the image for the localization of this source, with the location of the FRB shown with the white markers, and the white circle enclosing 90% of the optical light from the globular cluster. This source is different from the one that I was previously talking about because no periodicity has been detected in burst arrival times for this source. Now I'll move on to the constraints from population studies, starting with propagation effects. So a lot of FRBs are known to exhibit high and variable RMs, starting with FRB 2012-1102A. This source had an RM of 100,000 radians per meter square when it was initially measured. And since then, the RM has been decreasing by about 15% per year. This is shown in the plot on the right with RM on the y-axis and the time on the x-axis.
5 minutes.
Yes, thanks. There is also FRB 2018-0916B. The RM of the source has increased by 50 radians per meter square. And then there is the other FRB with the persistent radio source, FRB 2019-0520B, whose RM has varied from 10,000 to minus 24,000 radians per meter square, with like the sign change indicating changes in the magnetic field orientation. These high and variable RMs suggest that FRBs are located in extremely magnetoionic environments, supporting progenitor models where the FRBs are located in the vicinity of supernova remnants, pulsar wind nebulae, or in the vicinity of a high-mass stellar companion. The CHIME FRB scattering distribution also suggests that FRBs are located in extremely turbulent environments, specifically environments that have more extreme properties than those of galactic pulsars. Then we have the subarc second localization. So precise localizations can help determine the proximity of a source to the neighboring star formation regions. So FRB 2018-0916B was found to be offset from a nearest stellar clump by 200 parsec. A neutron star needs greater than 800,000 years to be able to traverse this distance with average kick velocities. And this is inconsistent with the active age of magnetars, which is less than 10,000 years. It is more consistent with the age of high-mass X-ray binaries and their separations from the nearest OB associations. The plot on the right shows the location of FRB 2018-0916B in green, and the white arrow here indicates the nearby star formation region. FRB 2012-1102A also shows a similar offset, so about 200 parsec from the nearest stellar clump. However, the source is still within the half-light radius of the star-forming region. The constraints from HST observations of 8 FRBs with subarc second localizations are also giving rise to a similar picture in that most FRBs are not located in regions of high local star formation. An exception to this picture is FRB 2020-1124A. This source has an inferred star formation rate of 10 solar masses per year, indicating that it could be a young magnetar. The plot on the right shows the specific star formation rate on the y-axis and the stellar mass on the x-axis, with the pink point here way above the star-forming main sequence, indicating that this is a region of high star formation. Last, we have the host galaxy properties, which Tarane talked about in her previous talk. So I'll just briefly describe the constraints that we have on the progenitor models based on the host galaxy properties. So the host galaxies are found to be moderately star-forming, but do not track stellar mass or star formation. Additionally, the properties of FRB hosts are found to be indistinguishable from that of core collapse supernovae and short GRB hosts. However, we are starting to rule out some progenitor models based on the properties of host galaxies. For example, the stellar mass and the star formation rate of the known FRB host galaxies is inconsistent with hydrogen-poor superluminous supernovae. So we have some ideas of what FRB progenitors could be based on recent observations, but of course there is no clear picture emerging out of these observations. An isolated magnetar origin was supported by the SGR 1935 burst. However, the isolated magnetar model has some issues in that it cannot explain the periodicity of FRB 121102A, and it cannot explain the fact that FRB 2018-0916B is offset from the nearby star-forming region. So we do need more observations in order to say whether all FRBs have a single progenitor or whether there are two different kinds of progenitor models for FRBs. And the first kind of observation that we can do in order to answer this question is associating more FRBs with known transients. So the cross-correlation of CHIME-detected sources with other transients would, of course, help in this regard, as was shown in Alexandra's talk yesterday. We could also go a step further and perform low-latency follow-up of short or long GRBs, so interesting supernova events and gravitational wave events. Targeted FRB searches of nearby magnetars, X-ray binaries, and ULXs are also an option, because seeing an FRB associated with an X-ray binary or a ULX would at least tell us that there are two different progenitor models. So the other thing that can help is having a larger sample of host galaxies. This will help us quantifying whether there are differences in host properties of repeaters and non-repeaters, because currently the hosts of repeating and non-repeating FRBs are indistinguishable from each other. This might also help us group FRBs into different subpopulations and point at different progenitor models if different galaxies have different kinds of properties. Another thing that a larger sample of host galaxies will help us do is we can determine if their redshifts track the star formation rate, which can also tell us whether the progenitor comes from a young magnetar or has a more delayed formation channel. Other things that we are actively doing and should continue to focus on are long-term monitoring of repeating FRBs. So if we detect periodic activity windows in more FRBs, then we can differentiate between the isolated neutron star versus the interaction models. And the dispersion measure and the RM variation can also be compared with theoretical expectations to lend support to or rule out some progenitor models. Another avenue that we should continue pursuing is milli-arc-second localization of FRBs. This will help us determine spatial distributions within the hosts and comparing them with known transients, and also seeing the location of the FRB with respect to nearby star-forming regions. And it's a long shot, but for very nearby FRBs, we might, so deep imaging observations might enable identification of a stellar companion. So these are some of the ideas I had, but I'm happy to hear more ideas and answer any questions. Thanks.
Thanks, Pragya. Any questions?
Thanks for the great overview, Pragya. Has 12102 actually turned off? When was the last burst observed from it? This is relevant for some models for repeaters that actually predict turning off of FRBs from them.
So as for CHIME, we have only ever seen one burst from FRB 121102, and that's the only instrument that I know of that's like continuously monitoring the source location. There have been follow-up observations with Effelsberg, but I'm not aware when the last observation was and if there have been any.
Can any other observers
detections.
comment on when a last burst from 12102 was observed? When was the last burst detected from 12102?
Yeah, but I'm also asking when was it observed and not detected?
I don't know.
Yeah.
Yeah. Yeah, because this is relevant for models that involve creating sources that actually predict a slow turning off of repeaters. So, yeah.
Yeah, at this point, I think CHIME is the only one that's like still monitoring it, but we have like about 4 minutes of exposure on the source each day. So I don't think that's enough to detect many bursts.
Thank you.
There is a question from Ryan Shannon on Slack. Has the periodicity in 121102 firmed up?
So there was, like after the initial paper by you, Kostub, there was another paper by Marilyn Cruces, and that lent some more support to the periodicity in that there were observations that were done during active periods as well as the inactive periods, and the bursts were only detected in the active periods. So the significance has become a bit better. It is, of course, not at the level that we know the periodicity of FRB 2018-0916B. But yeah, it's become a lot better since the initial detection.
Okay. Thanks, Pragya, for the lovely talk. I had a question about selection biases. When we observe these really scattered FRBs and really variable RM measurements from galaxies, these places could have, we might be detecting FRBs which are particularly selected because of their location in their host galaxies, and there are of course observational biases from our telescopes. So can you comment a little bit more about that? How should we go about thinking around this?
So I feel like the observational biases will actually act in the other way. So if you have a very extremely magneto-ionic environment, it's it might make it harder to detect bursts because of the high local DM contribution and the high scattering. So the fact that we are seeing so many FRBs with high and variable RMs as well as high scattering times actually suggests that there might be a lot more. So I feel like it is fair to make statements about the FRB population based on these few sources, because the fact that we have detected these indicates that there could be a lot more because most of our biases act in that direction. Yeah.
Thank you.
All right, let's thank our speaker again. The next speaker is Akshatha Gopinath, and she'll be telling us about propagation effects in fast radio bursts as seen by the LOFAR telescope. I'll give you a 2-minute warning, Akshatha.
Sounds good. Hi, everybody. I'm Akshatha Gopinath, the second-year PhD student from the University of Amsterdam, working with Jason Hessels in the AstroFlash group. Today, I'll be talking about propagation effects in fast radio bursts as detected by the LOFAR telescope operating between 110 and 180 megahertz. The LOFAR telescope is nicely pictured in the background here. And as we all know, for the FRB to be detected by the telescope, it has to travel a long way through the local environment of the source, the ISM of the host galaxy, the IGM, and the ISM of the Milky Way. And as it travels through all these media, it undergoes a bunch of propagation effects that help us trace the local environment of the source. Now let's look at some of these propagation effects and what they do to an example burst pictured here on the left. First, we have drifting, which causes the subbursts at lower frequencies to arrive later in time as a linear function of the wavelength. Next, we have dispersion, of course, giving us a quadratic sweep. Once de-dispersed, we are left with a burst that is scattered, with scattering time scale being proportional to the 4th power of wavelength. Lastly, we have Faraday rotation. When the burst travels through a magnetized plasma, Faraday rotation causes the plane of polarization to rotate as it travels through this medium and gives us these oscillations in the Stokes parameters Q and U, which previously wouldn't have been present. Coming to what has been detected by LOFAR so far, Plunas et al. And Pastor Marazuela et al. Detected bursts from FRB2018-0916b, or R3 as we know it, between 110 and 180 megahertz again. And you can see a couple of example bursts from Plunas et al. Pictured here on the left. If you look at the second burst, you can see it extend down to the edge of the LOFAR bandwidth at 110 megahertz. So we know that the source environment was clean enough for to allow this. Now, we already knew that the source had a periodic activity of 16.33 days with a 5-day activity window at CHIME. When we plotted the LOFAR, when the LOFAR bursts were plotted up against the 16.33 day activity window in activity phase, we saw that the lower frequency LOFAR bursts arrived systematically later in phase compared to higher frequency bursts at CHIME FRB, GMRT, and aperitif at L band. Now, we wanted to see if this shift in activity window remained stable in time, and if the window itself, the size of the window itself also remained constant. So what we did was continue monitoring this source for a long time. In the big panel A here, you can see time on the x-axis, activity phase, time on the y-axis, activity phase on the x-axis. Lower half of the x-axis shows all the bursts detected by Plunas et al. Those were 18 bursts. and yeah, they're marked in orange. In this work, we, as you can see, continued monitoring the source for another 1.5 to 2 years. And in this time period, we detected 7 more bursts from the source. We see that all these bursts fell within the previously constrained activity window, and the shift delay towards lower frequencies in activity remained as well. What we saw, though, was that the burst rate seemed to have gone down during this nearly three years of monitoring. During the time period where Plunas et al. Detected bursts, on an average, during the cycles where bursts were detected, the burst rate was about 1 burst per hour, while in the new cycle of monitoring, we detected only about half the burst rate. These are some of the bursts, actually all the bursts detected during the new monitoring. And as you can see, the scattering tail is pretty pronounced at LOFAR frequencies. So we wanted to see if this was somehow affecting how well we could detect the bursts with LOFAR and causing this change in burst rate that we saw. Turns out, no, the scattering didn't show any obvious correlation with the decrease in burst rate. On the left, we have the scattering time versus time. And as you can see, there's various scattering times measured for bursts within the same activity cycle, which means it is probably not correlated with the changing burst rate between cycles.
2 minutes.
We also measured the subburst drift rate, which varied with frequency, and even within the LOFAR band, this was consistent with what is measured at higher frequencies. Another way to trace the local environment is through the Faraday rotation. We have RM versus time here, where the RM of the source remains stable for a long time. Again, the LOFAR bursts are in orange. And we saw this last point suddenly where we measured an RM change of 10 units. And we were quite surprised by it. But turns out, when Mckinven et al. Put out their results from RM measurements from CHIME, the LOFAR measurement of RM fit in very nicely with what Mckinven et al. Measured for the secular change in RM in recent times. We wanted to see if this change in RM was due to something I define as RM index here. Traditionally, RM is proportional to the square of the wavelength, inversely proportional to the square of the wavelength. And I define RM index as lambda bar n here, where n is the RM index. When I plotted RM versus RM index for this specific burst with a different RM, I saw that it peaked at an RM index of 2.15 instead of the traditional 2. This could be due to multipath scattering, causing a scatter in the RMs through these different paths as well. Now, we already knew depolarization in R3 occurred at LOFAR frequencies from Plunas et al. I also wanted to see if this depolarization can be seen even within a burst, so I divide up a single burst into 4 different bands. And when I measure the linear polarization profile for these chopped up bands, you can see the red profile decreasing in power as the frequency decreases. So we not only observe depolarization at LOFAR frequencies, we observe them between and within the bursts themselves. When I plot up all the linear polarization fractions for these, all the bursts that we could measure an RM for, we see that the frequency of depolarization is jumping around quite a bit. And if you look at B24 and B25, we see that even at the top of the LOFAR band, there are bursts that are depolarizing. Interestingly, these two bursts came after B23, which was the one with this anomalous RM measurement. This depolarization has been predicted, has been seen for other repeaters as well, shown by this nice figure in Feng et al. And I think models of depolarization can be differentiated between very nicely due to this depolarization we are seeing even within the bursts in the LOFAR band. That was my time, and this is a summary of all the propagation effects we measured. I'll take any questions now.
Thanks, Akshata. Any questions?
Hey, thank you. Can you say something about your choice of DM? It looked like the leading edge of some of those dynamic spectra were maybe not fully de-dispersed, but of course these things can be tricky. And also, does DM change at all when the RM went to minus 70?
Can you bring up the... yeah, so you're right that you do see this, you do see a linear trend left behind after it has been de-dispersed as well. And that's because at LOFAR frequencies, because the scattering time is so long, the subbursts can get, merged together and the structure is not very obvious. Mckinven et al. Measured DM changes of about 0.8 parsec per centimeter cube. So we didn't think it was significant enough to be incorporated.
Thanks.
Hi, great talk. I have two questions. The first one is a simple one. What is the average exposure that you do in every observation for 3?
About 5 hours per cycle.
Oh, okay, 5 hours. And can you be, would it be possible that the rate decrease that you see with LOFAR is correlated with the rate of CHIME?
Yeah, that is something I'm looking into. As you can see, I've plotted up the CHIME bursts, but the sample is not complete, so
okay.
We'll be calculating that next.
Yeah, cool, thanks.
Hi, great talk. I just want to ask, what are your limits on the rate you have calculated? Are the lower limits of the one consistent with the upper limit of the other? What's the?
They fall within 1 sigma, so I think we'd need more observations.
Oh, okay. Thank you.
All right, feel free to ask more questions on Slack. Let's thank our speaker again. Next up is Casey Law, and he's going to talk about finding FRB sources without FRBs. I'll give you a 2-minute warning, Casey.
Okay, thank you. Great. Thanks, everyone. Great to be here. So I'm Casey Law. I'm a scientist at Caltech, and I'm going to present finding FRB sources without FRBs, which might be also framed as studying transients without transients, because we're talking about persistent counterparts to FRBs. The persistent radio source phenomenon, which we've all actually heard a lot about this morning. Fantastic to hear all that great new results there. So I had intended to sort of advocate for people to sort of pursue these sources and sort of chase it down and help us understand the FRB phenomenon. But since there's so much work happening already this morning, maybe another outcome of this is to provide a little context and sort of extragalactic radio survey perspective on the phenomenon and what it means when we're talking about persistent radio sources. It's not just understanding the FRB source problem, but understanding how they contribute to our understanding of the radio sky. So this is work done with Liam Connor, who's here, and Jerome Seebeck, who's a finishing senior at Caltech, who's now starting at the University of Maryland as a graduate student. So I'll start with the provocative statement. Is it working? This one. Okay. Okay. Thank you. So, perhaps a provocative statement for this audience. There's nothing as useless as a radio source. So this is a quote by Jim Condon, who made his career out of studying radio sources. But as a part of the NREL VLA Sky Survey, pioneered the study of the radio sky. But the point is that, in many cases, the study of extragalactic radio sources is essentially measuring a single flux at a single time at a single frequency. And generally, these sources are compact, and so there's not a whole lot you can say other than that those sort of 2 or 3 numbers, RA dec, flux, frequency, maybe. And the value that Jim and many others have gotten out of these surveys is in the cross-match and the association of these sources with other wavelengths and other catalogs. And so through that analysis, people have established a basic understanding of what the radio sky looks like and what these sources are. And there's essentially this understanding that there are 2 kinds of radio sources. One is sources that are associated with star formation activity, so the combined effect of thermal emission from ionization from star formation plus supernovae, and then also AGN, so accreting supermassive black holes. And when you put the radio sources and classify them based on their cross-match, say with infrared catalogs or optical catalogs, you can actually measure the abundance of these sources, or the density, number density as a function of luminosity. And you tend to have some distribution like this, where you have AGN is very, very luminous. You see them out essentially to the edge of the universe, and then star-forming galaxies are relatively nearby. So that's sort of the common understanding, and this actually has been very fruitful because understanding the star formation history of the universe is extremely valuable for understanding the history of the universe. AGN are part of feedback that help us understand how galaxies grow and evolve. But what I'm here to tell you is that there's a new kid on the block, which is persistent radio sources. So we know there's not just 2 kinds of luminous sources that you can see in the extragalactic sky. There's actually a whole new category of source, which is this persistent radio source phenomenon. And the 2 that we've heard a lot about today are 2 that are well characterized and identified as compact and luminous and associated with an FRB, and that is the 121102 and 190520. And the process has generally been FRB localization, persistent radio source identification through deep radio imaging, and then characterization of the spectrum. And in both cases, they look quite similar to each other, which is helpful. And they don't look a whole lot like star formation or AGN. Sorry, it's not working now. Thank you. So we have this sort of exciting challenge and interesting challenge, which is that we have a double mystery. We don't know what FRBs are, we don't know what PRS are, and we don't know why they're found together. So last year at the FRB2021 conference, I presented some early results from this paper that we wrote up on the PRS phenomenon and thinking about what they mean as a contribution to the extragalactic radio sky. So one basic thing we do is to define the persistent radio source phenomenon as a compact source that has a luminosity of about 10 to the 29 ergs per second per hertz. So in this sort of classic extragalactic radio source distribution, it falls sort of near the gap between these 2 populations. And then we also thought a bit about how to estimate how common the PRS are in their association with fast radio bursts. And this is sort of a Venn diagram which shows where we know about FRBs that are localized well, which ones of those are repeating, and categorizing them as, and the limits that we have on the persistent counterparts there. And that's helped us to estimate a fraction that have persistent radio source counterparts that are meaningful. And then we also go into some considerations of how PRS and FRB properties are correlated, which we can talk about later, and some evidence that potentially PRS are preferentially associated with repeating FRBs. And then finally, we wanted to provide that sort of extragalactic, intuition. What is the count, the volumetric density of these sources, both in terms of the FRB sources and then the PRS sources in the universe? And to do that, we start with an equation like this, where we have the phi z, which is the FRB volumetric rate, so number per cubic gigaparsec per year. And we can, if you divide that by the repetition rate and a beaming fraction, you can actually calculate a density in terms of number per cubic gigaparsec. So that's a source density. And so when you go through the numbers, we have pretty good estimates. Many people have worked very hard on the phi-Z measurement, and we heard some of that earlier in this symposium. Liam had a nice approach to estimating the bound on the repetition rate of the population of all FRBs from the CHIME FRB sample. I can talk about that in a bit more detail. But essentially, it's bounded based on assumptions as to whether or not all FRBs repeat, or there's sort of two populations that repeat and do not repeat. And if you plug that in with an assumption of the beaming fraction, which is fairly uncertain, you can have an estimate of the volumetric density of something in the range of 2 times 10 to the 2 to up to 5 times 10 to the 4. And for reference, the density of, say, star-forming galaxies or AGN are something like tens, hundreds, to thousands times bigger than that. So the number density of FRB sources, so correcting for beaming, this is the actual source density, is something like 1% or 0.1% of those classic radio source populations.
2 minutes.
Thank you. And so another fun number to compare to is the number of magnetars. You can estimate that. It's actually 1 in a million magnetars in the universe. The density of FRB sources compared to magnetars is a very, very small number. So we can talk about that some more. And what makes this really valuable is that you can then just simply apply that to the, if you assume some volume-limited sample, you can think about how many radio sources you can see in existing radio catalogs. So this is where the extragalactic survey perspective comes in. So once you know the density of those sources and the number in the catalogs, you can go about it with basically catalog-based astrophysics. So the VLA Sky Survey is a great place to start. It's sensitive, it covers the whole sky. We have multiple epochs. And there are existing large catalogs of galaxies, including this GLADE Plus, which has 22 million catalogs, so sort of an agglomeration of many other surveys. So this is where Jerome Siebeck's senior thesis took over, developed a sample of dwarf galaxies, cross-matched them and used this AstroPath framework to associate radio sources from VLAS to GLADE Plus catalog. And then we're trying to sort and remove astrophysical foregrounds. And principally, we're trying to get rid of AGN because they're so much more numerous. So we're taking out the nuclear sources. And then also we have a luminosity cut, which is our definition of what an FRB is. And you have examples like this one here. But I think the basic message I want to send here is that we know now that there are many more than 2 kinds of radio sources in the universe, right? The PRS phenomenon. And we're not the only ones saying that. There is another good body of work in studying how AGN can be found in, or theoretically expected to be present in dwarf galaxies based on the formation of galaxies. And so you should expect accreting supermassive black holes in small galaxies that are not nuclear. So potentially those are relevant here in a confusing foreground. But also there's some great stuff happening in the Caltech group. Actually, Dylan Dong has finishing up his thesis at Caltech and has found an incredible source through a VLAS transient search approach, which looks an awful lot like a pulsar of a nebula or a very high magnetic field spin-down powered radio transient. And then, of course, on the theoretical side, there's great work that demonstrates that there are reasons to expect luminous counterparts to exotic and hypothesized sources. So these things are out there, and so we just have to go out finding them and sorting them out from the astrophysical foregrounds. And so this is sort of a status update on what we're doing with Johnny's Jerome Siebeck's catalog. So we're elaborating on his catalog and going after it with multi-wavelength radio catalog, so adding in other radio surveys. And we're identifying unusually flat radio spectra. So this is a luminosity versus spectral index plot, which shows how the radio sample that we've identified sort of stands out in terms of this space. And so things to the left of this are inconsistent with diffusive shock acceleration that you might expect from, say, AGN or other processes. And they are consistent with the PRS sample we know of and Dylan's new VT1137 source. But ultimately, the best way to characterize and confirm that these things are inconsistent with most other astrophysical foregrounds is through VLBI. We want to find that these things are parsec-scaled sources. So we're going after this with VLBI as well. And so to conclude, just note that PRS are an ubiquitous phenomenon, if not 100% association with every FRB. We know that they're a common aspect of every FRB, perhaps as a normal phase of life or certain class of FRB. And we can find them out in the local universe readily, if we know how to look for them. And the extragalactic radio sky is more diverse and interesting, and catalogs are helping us access that. And finally, through VLBI and other techniques, we can hopefully sort out the confusion and help us identify new PRS sources. I'll stop there. Thanks.
Time for one quick question, only if it's quick.
Hi, thank you. So if the dwarf galaxies are in the northern sky, then CHIME would have probably detected them. So how would this play into that?
Sorry, can you say it again?
If the candidates are in the northern sky, then they would have been, if there are any FRBs from them, they would have been detected by CHIME. So how would this play into non-detection by CHIME would play here?
Well, saying that we should have detected an FRB is I'm not sure that's true necessarily, because there are lots of sources that would not be detectable by a particular frequency potentially, or they're not active at the right time. But that would be the gold standard, is to find the persistent radio source and then identify an FRB afterwards. That would of course be the definitive proof. But in the absence of that, we're relying on the process of elimination and removing the astrophysical confusion and saying that we know this is a compact source that's inconsistent with star formation, AGN, and all the other sources.
Yep. Thank you.
All right, let's thank Casey again. And next, we have a remote talk by Danica Scott, and she'll be talking about the high time resolution CRAFT FRB sample. I'll give you a 2-minute warning, Danica.
Am I good to go?
Yeah, we can hear you. I can see the
Awesome.
slides. Yeah.
Awesome. All right. Yeah. Hi, everyone. My name is Danica. I'm a third-year PhD student at Curtin University, and I'm a part of the CRAFT collaboration. And I'll be talking about the high time resolution CRAFT FRB sample. CRAFT is able to, using ASCAP, from incoherent detections, from real-time incoherent detections with ASCAP at about 1 gigahertz, we are able to save raw antenna voltages of a duration of about 3 seconds in each antenna in 2 different polarizations, which allows us for one-off FRBs, or for any FRB that we detect in real time, obtain arcsecond localizations through interferometry, and also 3 nanosecond polarimetric data with very high signal to noise due to coherent summation and signal processing. So I'll be talking about the high time resolution data. So just quickly on the, oops, is this working? There we go. Okay, just quickly on the process itself, so ASCAP is constantly, CRAFT constantly has in the background of almost all ASCAP observations a real-time incoherent search going for FRBs. When the search detects an FRB candidate above the thresholds, a ring buffer that is saving about 3 seconds of a 336 megahertz band of voltages is triggered, and the voltages are saved. And then from these voltages, we obtain the localizations, do beamforming, invert the channelization, and all that to get ultimately very high time resolution data products and arcsecond localizations. The data, just to give you an idea of the, what is, incoherent versus coherent. On the left here, this is a dynamic spectrum of an FRB at a 1 millisecond time resolution. This is what's typical for incoherent systems. And in fact, this is what our search algorithm is currently searching over at this approximate time resolution. But through the voltage dumping and beamforming, we can get something that looks a lot more like this. This is plotted at 20 microseconds. This is the same FRB. This is not as high as the time resolution can go. It can go a factor of 20 higher at the same frequency resolution. It's just been averaged because that's what's most convenient to see this FRB. And as you can see, you can resolve out, all the fine structure within the burst that is previously completely inobtainable. At the moment, we have a sample of about 10 of these FRBs that are, actually processed in this way, with several more to come, and full, results and analysis of the burst properties to come as well. I've just shown the ones that we have here. As you can see, we get a wide range of different burst types over different durations. Notice that each of these plots is plotted with a different time resolution. Produce this data is quite an involved process. And over the past few years, as we've been developing it, each of these processes, which I've just represented on the right there, the details don't matter, but the point is that there's a lot of different processes that used to be done sort of one at a time while we were figuring out how this all worked. But my job basically starting 2 years ago was to automate it, which I thought would be easy, but I'm still not done. And basically I have this slide to proselytize a little bit about Nextflow. If you have a complicated data processing pipeline that is currently glued together with bash scripts, I really, really encourage you to check out Nextflow. It will make your life a lot better, basically straight away. And part of why this automation was important is not only because it makes our lives easier by not having to handle the data manually. It also is going to be important for the next era of ASCAP FRB science when Krakow starts to change our search, a real-time search from an incoherent one to a coherent one, which will increase our rate of FRB detections from of order 1 a month to of order 1 a day. So you can't exactly have 5 PhD students just manually processing all the data. It'd be much better to have one PhD student make an algorithm, a pipeline that can do it automatically. And this pipeline I've recently named the CRAFT Effortless Localization and Enhanced Burst Inspection Pipeline, which I'm very proud of as an acronym. This pipeline is a combination of a lot of other people's work. Most importantly, these people on the screen. Development's still ongoing, and it requires a lot of computing resources from both Aussie and Ulster. But to move on to the science before I run out of time, obviously we do all this processing because we want to do science with this high time resolution data. Some of this has already been published. I will direct you to Kieran Cho and Cherry's Days papers from 2020 for the first 6 FRBs published in this of this data. Some of the things that we intend to glean from this data is information about the host environments by combining the scattering and scintillation, which you can see in this dynamic spectrum on the right, is in the time and frequency profiles. By combining rotation measures and dispersion measures, we can learn about magnetic field orientations around the source. And if there's differential DMs between components, it can tell us stuff about multipath propagation of the burst as it's traveling through. Another exciting thing that we hope to look into is coherence of FRB emission. This is possible because our data goes down to the 3 nanosecond level, and for many FRBs, because of coherent signal summation, we have often significant signal in 3 nanosecond samples, which is what I've shown on the right here. This is the time profile, the intensity profile of FRB 18, 11, 12 at 3 nanoseconds. And as you can see, there are, in individual samples, there is significant signal that we hope to glean through the statistics of this intensity, glean information about the emission mechanism at the source. Big problem with this is that dispersion is a really big problem at 3 nanoseconds. You need your DM right to about 10 to the minus 6 parsecs per centimeter cubed to eliminate DM smearing. Which is quite a difficult thing to do. Basically, the only way you can do it is by trialing millions of DMs and seeing if any of them give you interesting statistics. Obviously, you can't do that just over billions and billions of different DMs because that would just require too much processing. So you need to know somewhere to start.
You have 2 minutes.
Thank you. So we, instead of the sort of, I guess, the default easiest thing to do is usually to find the DM that maximizes signal to noise of a burst. So this is what's represented in the dynamic spectrum on the left. This is FRB202217. And this is what the dynamic spectrum looks like if you maximize the signal by summing just over the intensities. But if you instead maximize structure, which we do by maximizing the quantity di on dt squared summed, you can get different structure, which in this case is resolved out as a third little component in the main peak. And this is at a DM difference of about 0.2, which is 200,000 DM trials away from the signal to noise maximizing one, so quite a distance. A big problem with this is that we have a derivative here, and if you use a derivative on noisy data, you just get a lot more noise. So instead of doing the derivative of the data itself, we do the derivative of a smoothed data, which we smooth by regularization. But this raises some questions. It's how much should you actually smooth, and what is the error on the structure maximizing DM that you get after you smooth? These things are sort of not really obvious. But by representing the regularization smoothing process as a matrix operation, which is basically, so regularization, I've got a bit ahead of myself. Regularization smoothing is basically a smoothing method that balances goodness of fit with the smoothness of curve. And you can turn this dial all the way one way, all the way the other, depending on how much you want the data to be smoothed effectively. It acts a lot like a low pass filter. You can think of it that way. And by representing it as a matrix operation on your data, you are able to not only quantify what the best balance is, but also the uncertainty in the DM that you find. So on the right here, the top plot is the square root of that structure maximizing quantity for FRB 210117 versus the differential DM relative to the signal to noise maximizing DM. As you can see, that curve peaks at delta DM of minus 0.2. And the bottom panel is the uncertainty that is obtained through the representing it as a matrix and using linear algebra operations. This is being prepared in a paper led by my supervisor, Adrian Zutinho. It's in prep and will be hopefully coming out soon. So I'll just leave you with my summary, and I'm happy to take any questions.
Thanks, Danica. Any questions? So on Slack, Jason Hessels has asked, nice talk. Do you think it's possible that the bursts you have analyzed at high time resolution don't resolve to microshots because these are the wide bursts that were found at 1 millisecond time resolution? Also, have you done any high time res polarimetry yet?
Those are some good questions. So in regards to the polarimetry, there are in Cherry Day and Kieran Joe's papers, there is preliminary results for 6 FRBs. It hasn't been generalized out to the whole sample yet. And it's not at 3 nanosecond level. But to maybe could you just repeat the first question?
Do you think it's possible that the bursts you have analyzed at high time resolution don't resolve to microshots because these are wide bursts that were found at 1 millisecond time resolution?
That's an interesting question. I'm not exactly sure how to answer it. I do know that we do get a variety of bursts. It's not like the only bursts that ASCAP is detecting is just these wide broadband bursts. Like for instance, 190711 is a sad trombone-like FRB, and we do find repeating FRBs. We've observed 2011 24A with several repeat bursts from that. And there are other FRBs that we expect to be repeaters as well. But yeah, I might just continue the discussion with Jason offline. I'm not quite sure how to answer that just off the top of my head.
All right, thanks. We'll just do one more question.
Well, it's sort of a related question, but I was wondering if you ignored the events that are clearly scattered, what fraction of your bursts have microsecond structure when you look at high time resolution? Is it, yeah, I can't tell from your plots because a lot of them look kind of scattered, but.
Yeah, the scattering is present in obviously some of our bursts, but not all of them. I mean, like this is actually the almost complete sample of currently processed bursts. There are quite a few more that haven't been fully processed and got to the ends to this point yet. But yeah, on this plot, I would say that there are at least 3 typical bursts that have these very, very narrow structures on the scale of 10 microseconds and multiple components that aren't scattered, that have very, very little scattering. So yeah, hope that answers your question.
No. I was saying if you ignore the ones that are scattered, I was asking what fraction of events that you detect in the incoherent mode you then see microstructure, some sort of microstructure in when you look at high time resolution. Is it all of them? Is it 90%, 10%? That's what I'm asking.
I would say if there's no scattering, definitely more often than not. We also haven't fully, answered the question of whether or not the width of profiles is necessarily to do with scattering. Like in certain instances, like we haven't fit for Kolmogorov turbulence and like the complete set yet. That sort of, full suite of parameters measured hasn't happened yet because the sample is still not complete, I would say.
All right, let's thank our speaker again. All right, next we have Jakob Faber, who's going to talk remotely on compelling morphologies of fast radio bursts with CHIME FRB baseband data. I'll give you a 2-minute warning, Jakob.
Sounds good. Can you hear me all right?
Yeah.
Awesome. Great. Hi, everyone. Thank you all for coming. My name is Jakob Faber, and I'm currently wrapping up a year of working with the CHIME FRB collaboration as a post-bac Fulbright scholar, supervised by Professor Vicky Caspi at McGill and Dr. Daniela McKeely at MIT. And as of this month, I'll be a first-year PhD student at Caltech. So today I'm going to be telling you a little bit about some rather intriguing morphologies that we're currently uncovering and studying with CHIME FRB baseband data. But before I dive in, just to briefly introduce the topic, FRB morphology is, simply put, the change in flux as a function of frequency and time, or plainly time frequency structure. So in general, for all FRBs, this observed structure is shaped by some unknown emission mechanism and then transformed by propagation through some ionized, inhomogeneous intervening medium, which can cause things like scattering, scintillation, potentially plasma lensing. But in order to access the information that this burst structure carries, these effects need to be disentangled from each other. But doing so is rather difficult. So as a start, there are various overarching morphological archetypes that we can distinguish from each other. And one of the broadest morphological distinctions or dichotomies that we've identified is that between repeating and non-repeating sources. So non-repeating or one-off sources tend to be narrower in time and broadband, whereas repeating sources tend to be a bit wider in time, narrower in bandwidth, and they often contain some form of substructure or multiple subcomponents that can evolve in frequency over time. And so this evolution tends to be or can be observed as a sort of semi-linear downward drift in frequency over time, the sad trombone effect that I'm sure many of you have heard about. But so these types of bursts we label just rather sweepingly as complex. But so the reason that we're able to recognize this dichotomy is thanks to the wonderful instrument known as CHIME, which some of my colleagues have already talked about. So I'll try not to repeat what they said, but CHIME, and then again, the powerful CHIME FRB backend, which has graciously brought us thousands of FRB detections over the last few years. And in short, CHIME FRB searches in real time for fast transients in polarization summed intensity data at a coarse 1 millisecond temporal resolution, which for sufficiently bright bursts is then followed by a triggered baseband system that records the coherent electric field measured by each antenna in the CHIME array at the time of detection. And it's by processing and analyzing these full array baseband data recordings that we're able to perform source localizations with sub-arc minute precision, and most importantly for my purposes, resolve temporal substructure and polarization properties on a microsecond scale. So here, for instance, you can see the time frequency spectrum or waterfall plot for one of the more interesting events in the sample that I'm about to show you at a coarse 1 millisecond time resolution, which is again the resolution that CHIME FRB searches at. But sort of as we move to higher resolutions, we can start to see all these rich complexities emerge, like this one component here that I've outlined in red. This is only about 15 microseconds wide. And at this point, you might be thinking to yourself, surely the DM is underestimated here. However, this event has actually been dedispersed to a nominal DM that we've obtained from this narrow leading feature that I've outlined. And furthermore, the drifting that you're starting to see here does not appear to correspond to the cold plasma dispersion relation. So just bear with me. And as we get to the highest resolution possible with baseband data, namely 2.56 microseconds, we see that this burst is not only drifting, it's drifting non-linearly. It's drifting according to a power law, apparently according to a power law in time, which is something we have yet to observe this narrowly and in this much detail. More fascinatingly even, this type of power law drifting morphology was actually proposed less than a year ago by a professor named Brian Metzger at Columbia University and colleagues in the form of a toy model for FRB time frequency structure, which was initially motivated by, but not necessarily limited to, relativistic shock emission models. So the model, I won't go into too much detail on this, but the model effectively suggests that both frequency and luminosity of the burst decay according to power laws in time. Here, however, for what I'm presenting here, we're solely looking at the decay and the central frequency of the spectral energy distribution of the burst, and not the luminosity. But in the synchrotron maser shock model, for instance, the decay would occur as a consequence of the shock sort of decelerating and probing lower densities further and further away from the central engine. I'll note that magnetospheric models could supposedly account for this as well through raised frequency mapping, but this seems less likely here because what it all comes down to is this power law index beta, the index of the frequency drift rate, which is related to the radial density profile of the upstream medium. For relativistic shock scenarios, depending on the radial density, this index can change from around 0.2 to around 0.7. And just as a first pass of fitting this model to our data, using a rather simple method of looking at sort of the sub-banded time series with sort of masking out this, as you can see, there's actually two components, masking out this first one, we arrived at an index of around 0.78, which is on the outer edge of that range, but perhaps suggestive. It's worth noting, however, that this power law only describes the time evolution of the overall burst envelope, so not the substructure within it. So Metzger actually suggested that this substructure could potentially originate from some sort of propagation effect. As you can see, this image here that I borrowed from their paper, this contains some sort of blobby structure, and that's just subbursts that have been simulated by a periodic Gaussian filter, so nothing really physical, just to give kind of a visual sense. But this model, if it does indeed apply to our data, it could potentially suggest that the substructure present in our event isn't intrinsic, but that the overall envelope maybe is. All of that said, this is a rather exciting clue that favors a compact object progenitor and perhaps a shock emission model as well. But this is not the only confounding burst that we've seen. Not by a long shot. By searching through hundreds of bursts for which we have baseband data available with CHIME FRB, we've accumulated a select few, a rogues gallery of some of the sufficiently bright bursts that exhibit some of the most complex morphologies we've seen. And note that all of these events are currently one-off events, so as of yet one-off events. But within this sample, there are a number of bursts that exhibit morphologies for which any potential models are far from obvious. And
minutes.
I'll show a few more closely to exhibit that exhibit certain properties so you can appreciate them in a bit more detail. But as you can see here, we have things like upward drifting going on. This one on the left here seems to maybe indicate some sort of happy trombone, but it's not clear if that's the correct interpretation, whereas the one on the right is potentially almost like the inverse of the Metzger model, where it almost looks like the burst envelope is drifting upwards in time and then kind of turning into upward drifting filaments later, almost solar flare-like behavior. Notice that this sort of triangular feature here is a spectral ghost. It's due to spectral leakage and non-physical. We have bursts like this one, where we see overlapping subbursts, almost twisted up like a pretzel, and perhaps DM ambiguities could be playing some sort of a role here. We have bursts of extremely narrow 5 to 10 microsecond subbursts that are kind of sputtering, and intermittent rapid emission is going on here with potentially some sort of tenuous power law drifting again. And we see subbursts that are extremely narrow, 10 to 20 microseconds, that are fully resolved here, which is quite beautiful. And just at a brief glance, this is something that we're currently still investigating. We're seeing a variety of features in polarization, but ones that we recognize. So, for instance, here we see bursts that are nearly effectively 100% linearly polarized with stable, flat polarization angles. And this, many thanks to Dr. Ryan Mckinven, who'll be following me in the next talk, and his student Jenny Sue for helping with this analysis. But we do have one confirmed PA swing so far that we've identified, although we're still working to sort of investigate whether we can identify potentially some RM variations across subbursts. But this comes down to sort of algorithmic work and working to distinguish sort of physical properties from systematics that we're dealing with. And just as a briefly conclude, the morphologies, the main takeaway here is that morphologies may be much more complex than previously thought at microsecond scales. And currently we're still working to study things like sub-millisecond quasi-periodicities, which seems like a logical next step given sort of, especially those sputtering bursts that you just saw, polarization again, and additionally, we're just working to sort of see what sorts of emission models we can use to potentially account for these features and what sort of propagation effects, potentially plasma lensing, we can kind of we can use as well to sort of account for some of these morphologies, and whether other bursts can be accounted for them by the Metzger model, or whether there are bursts that have no plausible explanation as of yet. All of these are very exciting things to realize. But yeah, I'll leave it there and I'll take any questions. Thank you.
Thanks, Jacob. Time for one quick question.
Thanks, Jacob. Just a quick comment. So if the burst is induced Compton scatter and is affected by the induced Compton scattering, our toy model predicts a beta value close to 0, which would mean that you would see a happy trombone-like structure, even though it is not exactly the case. So yeah, that's it. Thanks.
Okay.
All right, let's thank our speaker again. And for the last talk of the session, we have Ryan Mckinven, and it's going to be a remote talk on multi-year polarimetric monitoring of repeating CHIME FRB sources. I'll give you a 2-minute warning, Ryan.
Great. Let me just throw this over here. Everyone can hear me?
Yeah, we can hear you. But your slides are not in the slideshow mode.
Oh, I think I know what the issue is.
I think you're sharing the wrong screen because we can see the presenter mode.
How's that?
Yeah, that's good.
Okay, great. Just, what's this? Okay, well, hi everyone. My name is Ryan Mckinven. I'm a postdoc here at McGill University working within the CHIME collaboration. And today I'm going to talk to you about some results from a polarimetric campaign monitoring a sample of CHIME FRB repeating sources. So when discussing FRB polarization, I think we've gone over most of the relevant properties from previous presentations, but it doesn't help to, it helps to refresh. When discussing polarization, we're mainly discussing three observables. The first observable, of course, is the polarization fraction, and polarized emission can be decomposed into two polarized modes, linear and circular polarized. And what we've seen from FRBs thus far is that FRBs tend to be highly linearly polarized, although recent observations have shown that circular polarization can be actually fairly significant. And this has been borne out in recent observations from the FAST collaboration of FRB 2011-24A, where they were able to leverage their high sensitivity to look at polarimetric properties of 1,800 bursts from the same source. And what we've seen is that the polarized fraction could be actually quite variable, changing significantly in both linear and circular. And in fact, the circular polarization can be in excess of 75%. So these observations, as we collect more data, will definitely kind of inform our understanding of exactly the precise emission mechanism and analogous galactic sources. In addition to polarization fraction, there's also, of course, the polarization position angle, which has already been mentioned in previous talks. And just very briefly, this just characterizes the intrinsic geometry of the emission at the source. And what we've seen from FRBs thus far is a pretty diverse range of behavior, with some sources displaying very significant change in the polarization angle over the burst duration, while other bursts apparently display relatively flat PA curves over the burst duration. One note on those sources that do display flat PA curves, when we've revisited some of those sources at higher time resolution, what we've seen is that oftentimes they display subtle PA variability on very short time scales. And this is shown here in the bottom panel here for 1809 16B from recent observations led by Kenzie and Nemo. And then finally, of course, the Faraday rotation measure is, of course, relevant here as a probe of the intervening plasma, picking up contributions from the host galaxy contribution that included the local environment, as well as a small contribution from the intervening intergalactic medium, any intervening source, any intervening galaxies, as well as the contaminant contribution from our own Milky Way. And what we've seen so far from the relatively modest sample of rotation measures that we've collected from FRBs is that they explore quite a large range of RM bodies, with some FRB sources displaying relatively modest RMs that are consistent with what we see from the galactic pulsar sample. But a small subsample of repeating sources that do display significantly large RMs that would indicate a large contribution from the local environment. So why study repeating sources in particular from the perspective of polarization? Well, repeating sources offer the opportunity for multi-epoch observations. And of course, this offers the opportunity to look at any evolution in the RM or DM or any other property as a function of time. And what we've seen from observations of repeating sources is that RM variability appears to be a fairly ubiquitous feature in repeaters. This was first seen from multi-epoch observations from 121102A, where we see a monotonic decrease in the RM over multi-year time scales that has been interpreted from various kind of progenitor model systems. One being, I suppose, one popular model being a evolving young supernova remnant as the source of the evolving rotation measure. More recently, I think what we've seen that's been interesting is that oftentimes these RM variability is not monotonic and fairly stochastic. And this is a good example of this has been the recent polarimetric observations from 1905 20b, where we see the RM actually switch sign, which clearly indicates that the source of the RM variability is from a change in the magnetic field rather than the local electron density. So it's really, at least for some repeating sources, it's really a change in the local B field that is driving the RM variations. So in addition to multi-epoch observations, of course, repeating sources also allow us to look at, to capture bursts over a range of frequencies. And this is valuable for looking for any sort of depolarization effects. And so this has been mentioned in several previous presentations, but we do see a systematic effect where the linear polarization fraction appears to be systematically lower at lower frequencies for a handful of repeaters where we do have the data available. And this has been interpreted as a depolarization effect of the effect of multipath propagation through a magnetized medium that has a stochastic contribution, which leads to depolarization becoming more prominent at lower frequencies. So kind of moving forward from there, these conclusions have been drawn with a fairly modest sample. The goal moving forward, I guess, is to collect more data, and this is of course where CHIME is kind of well positioned in the fact that it will and continues to collect new repeating sources and has a design that allows it to capture many repeat bursts over significant observing intervals. So the focus of my talk today is basically filling in the current gap, which currently exists, and reporting on polarization properties from the current published sample of CHIME FRB repeating sources. So what is this? Oh, okay. So what is this current sample? The sample is 18 sources. I'm reporting on the baseband detections, which whittles the sample down to only 13 sources. The sample is dominated by two prolific repeating sources, R3 and R17. R3, we've collected 44 baseband detections over a span of 3 years, and R17, we have 20 baseband detections. And this gives us a total sample of 100 baseband detections, and we detect RMs from 80 of those sources. For 19 of these 13 sources, these are the first polarization measurements. So one of the motivating factors, I guess, behind collecting this data is, of course, in the case of R3, constraining the source of the periodicity that we observe from R3. And here, polarization is potentially a very useful observable in that several of the models that have been put forth make implicit, if not explicit predictions on the evolution of the polarization as a function of time. In the case of an orbital model, you can imagine that an RM imprint could be tied to the orbital phase, whereas in the case of a precessional model, you can imagine that there'd be an imprint on the PA as a function of the burst phase. So just very quickly, stepping through what we've seen from R3, which is by far their most prolific source. The properties that we're tracking are the RM, the structure optimized DM, the linear polarization fraction, the burst subband, as well as the phase position within the 16.3 day cycle. And the main take-home message from our observations of R3 is that we observe a significant change in the RM behavior, particularly over the last 10 months or so, where the RM has changed its evolution into a secularly evolving RM, where it's changed by as much as 50 RM units and doesn't appear to be correlated with any DM change. This puts constraints on the magnetic field strength in the local environment, and we don't see any significant relation to the phase location, any phase dependence. In addition to that, we also observed R17, which is again another prolific source. We see significant variability in linear polarization fraction, and we see even more extreme RM evolution, with the RM changing by as much as 500 RM units over 2-year time spans. And again, we don't see any correlated evolution in the DM, which allows us to put some preliminary constraints potentially on the strength of the magnetic field in the local environment that can be compared to other repeaters, as well as any galactic analogs. And then very quickly, just quickly showing the other repeating sources where we've collected the data, just to drive home the point that the remaining sources tend to be sparsely sampled in time, making it a bit ambiguous about the interpretation of the RM evolution. But we do see sources displaying significant RM changes. And in general, we don't see any significant correlation in the DM. So it appears, again, that what's driving the RM variability is a change in the local magnetic field rather than the local electron density. And I believe I'm a bit over time, so I'm gonna skip ahead and just quickly show the depolarization plots of a handful of our repeating sources. So these are just updated plots of the handful of sources where we do have multi-band observations, showing the addition of the most recent CHIME observations. And what we see is that the polarization behavior is consistent with what we would expect from depolarization. If depolarization is a significant effect on the polarization fraction. However, we also see significant excursions relative to the best fit models that have been previously determined. So it appears that there's also intrinsic variability from the source itself that can be fairly significant. And I believe I'm over time, so I'll just leave up my summary slides and take any questions.
Thanks, Ryan. Time for just one very, very quick question. Otherwise, all right. If not, then okay. We have a very quick question, hopefully.
Thank you, Ryan. It's Jackie here. So you showed the plot showing the sigma RM of the FRB. So to my understanding, most of the FRBs are believed to be pencil beams. And if we detect sigma RM, I wonder what can we say about the foreground screen that is the turbulence scale of the foreground screen that is causing the sigma RM.
Right. Well, I think there's definitely some limits that can be put on the size of the turbulent eddies that are responsible for the depolarization under certain assumptions. The thing to keep in mind, I guess, is that there's also not just one depolarization model that could be responsible for the observed systematic effect that we're seeing. In fact, we can get depolarization from a simple RM gradient rather than any sort of a fully disordered magnetic field. So I think there's still a need for more data in order to constrain exactly the precise nature of the depolarizing foreground screen at this point.
Thank you.
All right. Please feel free to continue discussion on the Slack channel. Let's thank all our speakers from this session again. And we'll be returning here at 3:15 p.m.